I'm going to walk you through engine design for a 747. So you're going to have to design your engine using the enginesim, and hopefully now you figured out how to get into enginesim using the previous tutorial if you hadn't been able to get in there with Java settings. So it should look like this. We're going to walk through all the different options here. First, your flight specs, then inlet fan, compressor, burner, turbine, nozzle, and that's all of these components here. So this is what your initial screen should look like. Flight specs, a 747-400 typically cruises at a set speed and altitude, and that's given for you in the document. The throttle depends on if they're flying with or against a jet stream. So you'll type in that number here and then hit the enter key. Really important you hit enter, otherwise it doesn't save that information for speed, altitude, and throttle. Next, if you click up here on inlet, then you get into this inlet screen. Pressure can be lost from inlet to exhaust, especially at high speeds, due to sonic waves affecting airflow in the inlet, so you can have a pressure loss. This should remain at 1.0 for aircraft designed to fly at speeds less than 0.9 Mach. That's pressure recovery of 1.0. As speeds increase, pressure recovery drops, and so does overall efficiency. But we're going to be flying our 747 at less than 0.9 Mach, so we shouldn't have a problem. Again, as speed increases, as we get up into Mach speeds, then your pressure recovery, the amount of recovery that you can get through the inlet, drops, and so does efficiency, but we don't have to worry about that. So we're going to leave this set at 1.0. Now materials, that's something that you are going to change on each of these, and you need to figure that out based on your research. What does your research say is an appropriate material for the inlet? You have a lot of different options here which give you different densities and also different weights because they're different densities, and that's going to affect your overall engine efficiency. So let's click on the second one here on fan, and the bypass ratio is how much air passes around the compressor without entering it. A 1.0 represents a 1-to-1 ratio. So if you have a bypass ratio of 1, that means there's an equal amount of area passing around the outside of this as what's going in the middle. So that's a bypass ratio of 1.0. Now the pressure ratio is the pressure exiting the exhaust due to the pressure exiting the fan. Exhaust pressure is typically larger due to the compressor. Efficiency we want to keep at 1.0, that's optimum. In a commercial aircraft, what is the bypass ratio versus the pressure ratio? In a military aircraft, what's a bypass ratio versus a pressure ratio? So that's something that you could do a quick Google search for and see if you can figure out some information on there. I've given you some design specs that you have to keep your bypass ratio within. But hopefully your Google search is going to show you some information about how a bypass ratio is different between a commercial aircraft and a military aircraft. And that's pretty significant, pretty important piece of information, so make sure you Google that. Then also note the material that you're going to have to use for that one. Then we're into the compressor, that's this yellow part here. Lengthening the compressor can increase the pressure, which in turn increases the exiting temperature. And we want to have a big temperature differential between intake and exhaust, and that helps increase our efficiency and our thrust. So increased pressure and temperature helps fuel burn more efficiently, which means less fuel consumption. And we know that because of PV equals nRT, which you learn more about in physics and in chemistry. Pressure times the volume equals the number of moles times the universal gas constant times temperature. So what is a potential drawback of having a lengthened compressor, which means a lot higher temperature? So that's something that you might want to think about when you're looking at these materials. Well, if your compressor is longer than the temperature is higher, then that might mean you exceed your temperature limits. So that's something that you're going to have to play around with. You have to have a minimum number of compressor stages. I know that it shows that it's more efficient if you have less and less and less, but that's not realistic either. So we do have a minimum number in your design specs for compressor stages. And then again, you'll have to figure out what is your appropriate material options for a compressor in a turbofan engine. Then we have the burner. Burner, the fuel heating value is in BTU per pound. FHV is fuel heating value. Jet fuel is 18,000. Hydrogen is 49,000. We're using jet fuel, so make sure you keep it at Jet A. Temperature max is set to 2,500 degrees Celsius. This is the upper limit and cannot be safely increased with this given material. If you change the material, then your burner may be able to burn at a higher temperature. So that's something, again, that you might want to research, play around with, and see what is reasonable for a burner. Pressure ratios and efficiency, let's leave these at 1, but you can change your temperature max as long as your material allows that and is an acceptable material for your burner. Then the turbine, a 2-stage turbine, has 2 sets of nozzles. They allow air to pass through and aim it in a direction. And rotors, which turn as the air passes through. These allow pressure to drop from the increased pressure in the compressor, but keep the velocity nearly the same. And if you have more stages, you're going to get more pressure drop in this turbine right in here, this yellow component here. So if we look at this 2-stage pressure compounded impulse turbine, what we have is we have the velocity is starting to increase here, and with the increase in velocity we have a decrease in pressure. And then on this next stage of this rotor, we have a decrease in velocity of the air going through here as we get these rotors to turn. Then we have a set nozzle, which is directing the air, so that drops pressure again as velocity increases through this. And then the rotors, as it's causing the rotors turn, the air velocity drops, and but which doesn't affect the overall pressure because it's turning the rotors. So through these different stages, we can get a net overall pressure decrease where the velocity is just a small increase overall in this. And last is the nozzle. The nozzle is this back yellow component at the end here, and the size affects the mass airflow through the engine as it can restrict the air entering the inlet. If we close this down, then it's going to allow an overall reduced amount of air inside here. A larger nozzle generally increases the potential thrust, but it also increases the fuel flow, so then you're going to be a little bit less efficient. So modern jets for military aircraft can vary their exit nozzle size to allow for different changes in thrust and fuel flow. What you need to do then is figure out again the allowable material, and computing A8 divided by A2, that's the area of the nozzle, that's area of 8 divided by area of 2, your inlet. If we divide those two, you're going to see that we have a number less than 1 because this is a smaller number divided by a lot larger number. So that's a value that you can modify and see how that affects the desired outcome. So what is important on this? Your bypass ratio, your design specs on the document say it needs to be between 5.8 and 9 since we're doing a commercial aircraft. Those are typical values. Fuel flow, we're going to restrict it to less than or equal to 6,000 pounds per hour of fuel for our sim. The overall weight should be less than 6,000 pounds. The area, inlet area, we want to be between 40 and 42 square feet. Make sure you change that. And then your challenge is to find the best combination of the following: your net force divided by weight ratio, and your thrust-specific fuel consumption, which describes fuel efficiency of an engine with respect to the thrust output. So why would this be important, the net force divided by weight value? That's something that you might want to take a look at, research, maybe think about why is net force divided by weight important, and then also why fuel efficiency with respect to thrust output is an important value to consider. And those are the ones that we're going to try to design to make the best engine possible. That's what you have to do.